Welcome back. After two heavy DB videos, today's question is different. No formulas, just engineering judgment. Here is the setup. We have 6 telecommunication scenarios. For each one, you must pick the best transmission medium from twisted pair, coaxial, microwave, satellite, fiber optic, and free space optics. The scenarios: 1. Heavy telephone backbone traffic between two major Turkish cities. 2. An ADSL home internet connection. 3. Broadcasting Turkish TV channels to viewers in Germany. 4. A multimedia microwave link between two regional cities. 5. A 1 gigabit per second access link in a dense urban area. 6. Cable TV distribution in a city neighborhood. We will work through each one and explain not just the answer, but the reasoning. Before the answers, the framework. Picking a transmission medium comes down to 5 questions. Distance: how far does the signal need to travel? Bandwidth: how much data per second? Cost: capital expense plus operations. Mobility: stationary nodes or moving users. Coverage: point-to-point, point-to-multipoint, or broadcast to many. Match those 5 against what each medium does best. Twisted pair: short distance, low cost, existing infrastructure. Coaxial: short to medium, broadcast distribution, established for cable TV. Microwave: medium distance line of sight, terrestrial backbone, no trenching. Satellite: very long distance, broadcast coverage, expensive but reaches anywhere. Fiber optic: long distance, very high bandwidth, the gold standard for backbones. Free space optics: short distance, very high bandwidth, no license required but weather sensitive. Now apply this framework to each scenario. Scenario 1. Heavy telephone backbone, Istanbul to Izmir, about 500 kilometers. Long distance, very high bandwidth, point-to-point, stationary endpoints, cost amortized over millions of calls. Pick optical fiber. Fiber wins because at this distance, every other medium either loses too much signal or runs out of bandwidth. Microwave would need many repeater towers and is bandwidth limited. Satellite has the latency problem we covered last video. Fiber gives you tens of terabits per second over hundreds of kilometers. Scenario 2. A DSL home internet. Short distance, moderate bandwidth, and crucially, the infrastructure already exists. Pick twisted pair copper. We solved this in our midterm prep. Replacing the world's twisted pair with fiber would cost trillions. A DSL reuses the same copper that carries voice, delivering tens of megabits per second over a few kilometers. Reuse beats replace. Scenario 3. Broadcast Turkish TV channels to viewers in Germany. Very long distance, broadcast coverage, millions of receivers all over Europe. Pick satellite. Satellite is the only medium that can broadcast to a continent from one transmitter. Fiber would need a wired connection to every home in Germany. Microwave cannot bend around the curvature of the Earth at this distance. A single geostationary TV satellite covers a third of the planet. Yes, the propagation delay is 240 milliseconds end to end, but for one-way TV broadcast that does not matter. Scenario 4. Multimedia link from Mersin to Konya, a regional connection of a few hundred kilometers. Pick microwave. Mid-range distance, line of sight is achievable with a few repeater towers, and microwave avoids the cost of trenching for fiber. Bandwidth in the hundreds of megabits per second is enough for the multimedia traffic. Microwave is the practical, cost-effective middle ground for these regional hubs. Scenario 5. A 1 gigabit per second access link in a dense urban area. Short distance, very high bandwidth, rooftop to rooftop or building to building, and you cannot easily trench through a city. Pick free space optics. FSO sends a laser beam through air between two telescopes. It gives you fiber-like bandwidth, no trenching, no spectrum license, set up in days, not months. The downside is fog and heavy rain can drop the link, but for short urban hops, this is acceptable. Scenario 6. Cable TV distribution in a city neighborhood. Short distance, broadcast distribution to many homes, and existing infrastructure built over decades. Pick coaxial cable. Coax was designed exactly for this. High bandwidth, distributable to many taps along the same cable with the necessary shielding to carry TV channels. Modern hybrid fiber coaxial networks combine fiber backbones with coax to the home, but the last mile to the TV is still coaxial. All 6 answers, side by side. Heavy telephone backbone, Istanbul Izmir Optical Fiber for distance and bandwidth. ADSL home internet, twisted pair for the existing copper infrastructure. Turkish TV broadcast to Germany, satellite for continental broadcast coverage. Multimedia link, Mersin Konya Microwave for cost-effective mid-range. 1 gigabit access in dense city. Free space optics for high bandwidth without trenching. CATV neighborhood distribution. Coaxial cable for broadcast distribution. Notice the pattern. Each medium has a sweet spot defined by distance, bandwidth, cost, mobility, and coverage. There is no universally best technology. The right answer depends on the question. 3 takeaways. 1. Match the medium to the application. Every transmission technology has a sweet spot. None dominates everywhere. 2. Existing infrastructure is half the answer. Twisted pair survives because of ADSL. Coax survives because of cable TV. Building from scratch is expensive. Reuse what is already in the ground. 3. When in doubt, walk through the 5 questions. Distance, bandwidth, cost, mobility, coverage. The medium that best fits all 5 is your answer.